Hello and welcome back to this course. So last class we dealt with the significance of current density, significance of power density and how these parameters can be used to basically differentiate or rather compare the performances of different fuel cells as well as electrolyzers. And we also saw that as the area of the cell is smaller, we can expect better performances because there is less chaos in the system, and as and when the size of the cell increases, although the total current that is delivered by fuel cell is typically larger, but with respect to area, or when we normalize the performance with respect to area of the cell, we can expect it to be performing inferior compared to the smaller cells. So now the question arises whether we can go ahead with the smaller cells or the larger cells. So let's continue discussing with the power density. So wherein we take this two cells, let's say this is 5 centimeter square and this is, let me go ahead with 100 centimeter square cell, and as we have taken this example before as well, let me continue with that. And hopefully let's say this is giving maximum performance of in terms of current as 5 amperes. This current is in amperes, and this is, let's say, giving 100 amperes of current. So if I try to compare the performance at the same operating potential, let's say this is at 0.5 volt. So this could be giving roughly 2 amperes, and let's say this is going to give us around 50 amperes of current. So what I am trying to say here is, now which cell is to be used for the actual power applications. As we know, the function of any fuel cell is to basically provide maximum power or power to the particular load. So although the area with a smaller cell probably would be performing inferior, let me use this current density centimeter square. So if I normalize this, the power produced by, let's say, 5 centimeter square cell is at 0.5 volt, it is E times I. So it is 0.5 volt times, let's say it is 2 amperes of current. So this gives roughly 1 watt of power. This is P for 5 centimeter square. What is the case with the 100 centimeter square cell? So P100 is again E times I, which is 0.5 times 50, which is 25 watt. So if you look at the maximum power that is produced by any fuel cell or these fuel cells in this case, we can see that the power that is produced by larger area fuel cell, this is, let's say, 100 centimeter square, and this one is small 5 centimeter square cell. So larger area cell will by and large produce more power, and that is one of the reasons why you will see that in a lot of cases we have cells of larger areas, typically 300 centimeter square or 400 centimeter square, so that they can produce and deliver more power at whenever it is required. So let's go ahead and solve one more numerical with respect to electrolyzer. This time let's have one electrolyzer which is, say, performing at 1.75 volt. This is again potential, and the corresponding current is at around 100 amperes. So what we have been asked is, let's find out the volume of hydrogen produced for total electrical input, or total energy that is input is, let's say, around 1 kilowatt hour. So we have been given energy and we need to find out how much is the hydrogen produced for such electrical input, and we have also been given the performance curve. Let us start with the calculations. Let us first find out mass of the volume of hydrogen produced. We already know the formula, which is InV by NF. It is the same formula that we can use in case of fuel cells. In that case, this flow rate of hydrogen will be input to the cell, and the same formula can be used in case of electrolysis if you want to find out the hydrogen output. I forgot to mention the number of cells. Let's make our case simple. The number of cells in a stack is, let's say, 1. So, total current that is flowing in one cell is 100 amperes. Number of cells are 1. Molar volume is 22.4 liters divided by 2, and F is 96,485. So, that comes close to 0.0116 liters per second, which if I convert into an hourly basis, because the energy input is in kilowatt hour. So, let us first find out the volume flow rate of hydrogen produced. It is somewhere around 41.78 liters per hour. Okay. So, this is the hydrogen produced if I am operating the electrolyzer at the specific point, let us say 1.75 volt and supplying 100 amperes of current. So, that means the total power input is around 175 watt, and let us convert that into the energy, and then we will compare it the total energy input, that is 1 kilowatt hour with respect to this, and then we will find out the flow rate of hydrogen produced. Let us go ahead. So, let me write this up. So, power input is around, let us again potential versus current. So, potential is 1.75 volt, current is 100 amperes. So, that comes 175 watt. So, please, and let us highlight this fact that although the potential has to be entered in, or rather put in with minus sign as we have discussed before, but that minus sign only indicates that the energy is to be input. So, we can therefore neglect that negative sign here, and we can only say it is plus 1.75 multiplied by current, that is the total energy input will be, power input will be 175 watt. So, what is the total energy input if for 1 hour is basically 175 watt hour, right? And hydrogen produced, as we have already discussed, hydrogen produced in 1 hour is roughly 41.78, that is liters per hour. In other words, if I run this electrolyzer for a 1 hour, it is going to produce roughly 42 liters per hour. So, let us go ahead and compare with the total energy input as the problem. So, therefore, for 1 kilowatt hour input or energy input, the hydrogen produced is given by, so that will be 41.78 divided by 175 watt hour into 1000, that is watt hour. I can simplify this, I can write it here. So, 175 watt hour produce roughly 41.78 liters per hour, or I can say liters of hydrogen. So, 1 kilowatt hour, which is 1000 watt hour, will produce how much? So, that way we can find out it is roughly 238.74 liters. This will be the hydrogen produced, and of course, we can convert this again into mass flow rate. We can multiply this with the density, and we can find out the mass flow rate in grams per hour that the hydrogen can be produced with this kind of electrolyzer. So, let us move on and go ahead with the another topic. So far what we discussed in case of cell efficiencies, fuel cell basically. So, we know the thermodynamic efficiency is ratio of the Gibbs free energy with respect to the enthalpy at STP, and that is a very standard value. I can even write this and as a ratio of reversible cell potential with thermoneutral potential, and they are constant, they are fixed for hydrogen oxygen fuel cell, and the number is constant 83%. So, if you look at this enthalpy, which is, let me write this up, enthalpy of the reaction is 286 kilojoules per mole, right, and this is valid, or this is applicable when the temperature of the cell is less than 100 degrees Celsius. In other words, if the cell is operating, let me write it where, at temperature which is less than 100 degrees Celsius, the water that is produced, will be in liquid form. Let me write this here, or liquid form or liquid phase. So, in that case we can write enthalpy of the reaction as 286 kilojoules per mole. So, this efficiency is valid when the temperature of the cell is less than 100 degrees Celsius, because when the temperature is less than 100 degrees Celsius, as we know, the water will be in the liquid form, water that is produced in the fuel cell. Let me quickly draw this figure. As we all know, it is water. I am typically showing polymer electrolyte membrane based fuel cell, wherein the half cell reactions are H2 giving 2H plus 2 electrons, whereas at cathode, this is anode, and at cathode we expect half mole of oxygen plus protons plus electrons to give 1 mole of water. So, this water that I am talking here, this water which is produced at the cathode, if the cell temperature is less than 100 degrees Celsius, let me write T is less than 100 degrees Celsius, water will be produced in the liquid form. What happens if the temperature of a fuel cell is more than 100 degrees Celsius? So, if the temperature of the fuel cell is greater than 100 degrees Celsius, what happens is this water, what is produced after the reaction, so this water will absorb the energy, or rather it will absorb some energy and will get vaporized. And this energy that is absorbed by the water is basically latent heat, which is roughly 45 kilojoules per mole of water. So, in that case, the enthalpy of the reaction comes down to roughly 241 kilojoules per mole. And now, once this changes, so let me underline whatever we had discussed. So, if this temperature of cell is less than 100 degrees Celsius, this enthalpy of the reaction involving liquid water is called higher heating value. HHV, whereas this enthalpy of the reaction involving water vapor is called lower heating value, LHV. So, let us compare the two efficiencies. The first, wherein the conventional high heating value is used. So, that in that case enthalpy the efficiency will be delta G naught by delta H naught. We know this answer, it is 83%, right, and here the temperature is less than 100 degrees Celsius, whereas if we go for lower heating value, the efficiency is basically the enthalpy energy divided by the lower heating value, or let me write enthalpy of the reaction, LHV. This happens if the temperature is greater than 100 degrees Celsius. So, which of these two is to be used in actual calculations? So, in real practice or in practice, normally enthalpy or the efficiency that involves higher heating value is normally used, right. This is reaction LHV, sorry, HHV, right. So, we have been doing it right. We have been using this efficiency as 83%, and wherein the enthalpy of the reaction is the same, that is, it is higher heating value. Let us go ahead and start with the construction of the fuel cell. Fuel cell construction. And I am typically going to limit my discussions with respect to the low temperature polymer electrolyte membrane fuel cell for easy understanding. So, we know that there is an electrolyte, but now I am going to try to slightly make it more specific. This is the solid polymer which is used as an electrolyte. Then we have electrodes on both sides. This is our anode and cathode. We also have gaskets, or let me draw it with the different colors. The gasket basically surround the electrode such that there are no leakages in the fuel cell. As we know, in this type of fuel cell we typically use gaseous fuel, that is hydrogen and oxygen as well. So, we need to make sure that there are no leakages, and that is why we use the gaskets. So, this is my gasket. We also have something called as bipolar plate. Now, the bipolar plate is again very adjacent to the electrode, and it is basically is one that touches the electrode. So, it has got grooves and channels. And fuel cell or if you take an example of fuel cell or electrolyzer, both of these electrochemical systems, they are very symmetric in nature. So, whatever we expect or have on the, I can say, anodic side, similar things will be present on the cathodic side. So, this is your bipolar plate. Let me write it as bipolar plate. Okay. The catalyst, which basically takes care of the reactions on the both side, is exactly present at the interface of the electrode and the electrolyte. So, this is where the catalyst layer is present. It's very fine in dispersion, and we can roughly expect a thickness of 10 microns for the catalyst layer. What is surrounded by it or what is supported by it is the gas diffusion layer. So, let me draw gas diffusion layer in the different color. This is my gas diffusion layer. So, gas diffusion layer is highly porous in nature. Let me show gas diffusion layer on both sides. So, function of the gas diffusion layer is basically to distribute these gases more uniformly on the surface of the catalyst layer, as and when the gases pass through these channels of in the bipolar plate, they diffuse through this diffusion layer, and then they reach the catalyst sites or the catalyst layer where the actual reactions take place. So, this is my gas diffusion layer. It is also very widely known as GDL. Thickness of gas diffusion layer is typically around 500 microns, and this is where we have, so as you can see, the gases basically flow through these channels. So, we have hydrogen here and oxygen on this side. So, this also contains hydrogen and oxygen. So, then I will also include one more component there. It is the current collector, which is very, has a very good contact with the bipolar plate. And this is where the cell is connected. Right. Right. So, voltmeter is basically used to measure the voltage across or the potential across the terminals of the cell, and we have ammeter to basically measure the current that is flowing through the cell. And then we have, in some cases, we have this another component called as end plate. Let me show it with the black color. And this is how it is. So, here we have a 10 volts arrangement to basically clamp the entire system, hold the entire system very firmly, and this is my end plate. Since it is at the very end, this is called as end plate. Then let me show, this is the bipolar plate, this one as well as this one. Then we have the gas diffusion layer on both sides. The polymer electrolyte, which is used as an electrolyte itself has got typical thickness of around 50 to 100 microns. Again, let me underline, I am talking about the polymer electrolyte membrane based fuel cell. It can also be in some cases lower than 50 microns. And bipolar plate in single cell, when we have a single cell, we do not call this as a bipolar plate, it is a monopolar plate. Let me write this up. So, it is a monopolar plate in case of single cell, and this is how we can expect the cell to imagine. And then this entire cell, as I discussed earlier or mentioned earlier, we have the nuts and bolts across all the corners of the cell, so that the entire assembly can be held very firmly. So, this, as I have already mentioned, this is my catalyst layer. Let me write it here. Catalyst layer, which is this and this. This has typical thickness of 10 microns. These are very approximate numbers. And so, as we know, once the hydrogen is supplied on this side, so that this forms the anode. Hydrogen side is basically anode, and then we have the cathode where the oxygen is supplied, and whenever we have gases supplied on the respective electrodes at anode, we know that hydrogen gets oxidized to protons and electrons. These protons pass through this electrolyte and electrons pass through the external circuit. So, what is the process? So, whenever we have this oxidation of hydrogen that takes place at the catalyst layer, which is present at the anode side and this side, the electrons, once they are generated, they jump back towards the gas diffusion layer, which is also very highly electrically conducting. And once they reach the gas diffusion layer, these electrons are again taken to this monopolar plate or bipolar plate in case of the stacks, and through this plate they are again taken towards the current collector. So, I will mention that as well. So, this is our current collector. This one as well as the other one. So, once we have these electrons, once they reach the current collector, they can be taken to in the external circuit, and once they flow in the external circuit, that is where we get the current because of the potential difference that is there across those terminals. And at cathode, once they reach the current collector, from this current collector they again jump to bipolar plate. From bipolar plate they again reach the catalyst layer through gas diffusion layer, and at cathode, as we know, this protons through the electrolyte plus electrons through the circuit, external circuit, plus oxygen which is supplied through these channels combine together to form 1 mole of water. So, and this is how the reaction gets complete. We have to also understand that both of these reactions happen simultaneously. It is not that the first reaction takes place and then the second reaction occurs at the other electrode. Both of these reactions have to happen simultaneously in order to get current in the external circuit. So, this is how the fuel cell construction looks like. In the next class, we will also go through the actual fuel cell for a simpler demonstration and a better understanding. With that, I stop here and thank you all.